today we're going to talk about even in test and measurement, there's thorough practices of sensor calibration, verification, and maintenance. A lot of these topics can be an afterthought. And as a manufacturer of CAL systems and a provider of CAL services, we often hear the questions, why should I calibrate my sensors and how often do I have to? So we're going to kind of address some of these topics today. At the Modal Shop, we deal with a lot of accelerometers. So a lot of examples today we're going to be using in this presentation may focus on them, but the principles can be used across any sensor type. Modal Shop was founded in 1990. We're based in Cincinnati. We moved into our shiny new facility in 2020, and we're a world leader in dynamic sensor calibration systems and services, both for the lab and the field, as well as offering recal services and other programs, including ILC, where you send a sensor around like blind round robin style to compare your lab performance against other labs. And it's an ISO recommended practice, or depending on the discipline of what you're calibrating, it may be a requirement. It's an artist rendering of our shiny new building, but I guess we should probably update that with a real life photo. Joining me today is going to be Patrick Timmons. He is a BSME from Michigan Tech. He joined TMS in 2009. He's a CAL systems engineer. He's a national park traveler. He once sat in a cardboard box for hours on end on an off day at an in-house Christmas party. It was probably the hardest I've ever laughed in my life. I thought I threw out something. And he hates presentations where there's only text. Me? I've been using this picture all summer. I should have changed it up. BSME from the University of Cincinnati. Joined the Modal Shop in '99. I lead the system teams for both rental and recal services. I don't mind spoilers, and I'm not real patient. So often when I look at presentations, I worry, is this really going to apply to me? Is there going to be anything useful that I'm going to gain out of this presentation? Or do I have to sit for 30 more minutes just to find nothing's going to teach me anything? That sounds wrong. That's not really how I feel, but sometimes. So to provide the spoiler and give you the answer for how often you should recalibrate or calibrate your sensor, it depends. And I'm sorry. What we're going to do today is provide some tools to question your existing methodology and investigate maybe ways to improve. We're going to maybe give you some oversights that have been missed in your process. Or if anyone's new to metrology, we're going to provide some concepts and terms and things to be aware of. And also a nice definition of an interesting question is something that's open-ended that smart people can legitimately disagree about. I love that definition. This is definitely the case. At Modal Shop, we deal with tons of very capable test engineers, and this topic surfaces way more than you might expect. And also today we're going to briefly go over what is considered a calibration. And again, this may seem trivial, but it really is a similar exercise to the 5 whys, if you're familiar. Just keep asking why. But repeated asking of what is considered a calibration can help us determine root cause and help us better understand existing practices and a direction to go ahead. The question of why you recalibrate at all is basically make sure your sensor is still healthy and accurate. It may be required by a regulation or test purpose, or it just may be required to mitigate risk. Not required, it's best practices, or may be required. Which leads to the opposite question, which is kind of the core question of the day: why not recalibrate? The enemies of calibration, or the opposing forces of calibration, if you will, are often cost and downtime. Some people, if your particular version of on the spectrum is that you want to make sure your calibration is done all the time, you're going to be running up against cost reasons and downtime reasons nonstop. But it leads us to developing what the interval is. it really boils down to risk. Generally speaking, people, including Modal Shop, as part of our CAL series, we have a wildly popular web series or email series on CAL topics that's mailed out. And we've done a really good job of describing risk in one of two ways. Not many approaches really take a holistic both access approach until maybe it was kind of mandated by the ISO 17025 risk approach assessment that was in the 2017 update. So a modern approach really takes a look at both. Kind of start boilerplating this, making a simple business graph. In relation to calibration, if a measurement's made only to discover later that the sensor or your measurement channel was bad, what's the cost of invalidating that data or retaking it, if it's even possible? The answers to outcome or the severity range from low to extremely high cost of failure, and they kind of form the other important axis in the risk assessment plan. And I want to kind of go over a few examples to illustrate this point. So things that we're talking about, like, for example, let's say you had a test that was a simple learning experiment in the university measurements course. The cost of retaking the data may be completely negligible. Or is it? It may not. If your grade depends on it, then maybe the severity risk for you personally at that time may be major. It's kind of interesting to make sure you consider all stakeholders along the path as important factors when considering severity. In a more standard test where you have easy access and re-access to the system under test, coupled with redundancy in measurement channels, like may often be done in Modal, the cost of a single bad measurement may not be high. Let's say you're doing a big structural test and or a single channel test for something that's going to be set up for days or weeks or months. Let's say you were doing a structural test on a car, body in white or something. Maybe no problem to retest or, figure something out if a channel looks bad. You can start to see that the costs escalate rapidly depending on certain factors, though. What if the test structure is a prototype costing tens of millions of dollars? What's the financial carrying cost of holding on to that prototype for another day? With aerospace structures, that cost can kind of be extraordinary. So the severity, again, might be kind of major. And another extreme category is for one-time tests with only one opportunity to collect data, something like a rocket launch or a building implosion or certain large-scale explosive tests. In this situation, the measurement has to be right. Channels are checked, double-checked, calibrated, re-verified, and the data is backed up concurrently. You name it, and a pre-test verification is planned. And a final category is those measurements made for legal purposes. Health and human exposure measurement used in legal proceedings for noise or vibration need to withstand scrutiny of the legal system in assuring that the measurement and resulting analyses are correct. As an example, the difference between suitable output and correct measurements highlights one of the major design and performance differences in the microphone industry. I'm speaking into a microphone now, but it's just a communications grade mic meant to make sure I provided semi-intelligible output over a variety of environments and situations. Whereas a measurement grade mic is designed to give accurate output related to amplitude, frequency, content, and the phase. So in addition to the importance of calibration, as an example, acoustic instruments like sound level meters have type certification to ensure the necessary accuracy of the complete measurement channel. The other major consideration towards understanding what sensor calibration intervals are appropriate for a test comes from investigating how likely the sensor and really the entire measurement channel is to experience an issue. Understanding failure modes, causes, and how issues are manifested and seen in data is really key, as well as often overlooked things like what happens in the sensor's life between calibration and test. So let's kind of look over some likelihood of sensor failures. Uh, and again, for the sake of example, we may pick on accelerometers, but there's a great paper that we'll reference in our email follow-up to this that we love, that kind of discusses a lot of types of sensors and their primary faults. It was presented, I don't know, maybe a decade ago, and it should be viewed as a Bible when you're considering sensor failures. But if there's bias faults, which mean zero drift or shift, any change in output over time that's completely unrelated to the input environment or load. If there's any time drift, which is any change in sensor output just based on time. If there's any scaling, which is the variance in transducer output to the input ratio. Any noise or complete hard faults where it's just measuring something completely off, almost like by a DC value. And understanding how this is seen in the data is key. This is really kind of what makes people experts in their field, that they're able to troubleshoot failures like this. Looking at the fault causes is really one of your first steps into assessing likelihood. How often do you think you may have a shock event or a temperature event? Anything current-based that may affect your sensor. Is your sensor affected by time? Is it it doesn't occur often in the types of sensors that we primarily deal with at Modal Shop, but there certainly are sensors that are time affected, or any other external inputs that may affect something. So we're going to pick on these pork cells again for a bit and look at some of the faults. And as we go through these, think about how many of these fault examples might be found by using something like a single frequency, single amplitude handheld shaker just before a test. Not to dog it, this is a great example of field calibration, just verification of a channel. But think about these faults as we go over them and see how they may affect, see if they may be able to be found by this handheld calibrator. So damaged piezoelectric crystals generally occur from shock damage to the sensor during a test or in handling. It can affect scaling, cause frequency shifts, and really it's not often found with a handheld calibrator. Often the damage is done quite higher, and we'll show an example of that in a bit. Debonding of the crystal for an Excel, it describes like when the piezoelectric element in the substrate degrade over time. This can affect scaling and frequency changes, again, often seen at higher levels than might be tested with the handheld. And I do want to note, things like this, you kind of have to trust your vendor. It's the history and pedigree and know-how of the vendor that can kind of give you some reassurance that some of these faults will occur or won't occur based on how long they've been doing something and they're standing in the industry, really. Depolarization and temperature shifts. Depolarization of the sensing crystal can occur if the elements run to temps above the operating range, and it can result in scaling or complete fault of the sensor. Generally, piezoelectric elements are temperature sensitive even within their operating range, and scaling may occur. So check your specs and understand how it affects your test. And think about, would a handheld calibrator check this? Loss of hermetic seal. Generally, a sensor like this may be closed or welded. Damage to that sealing can compromise the low frequency performance, and low frequency scaling issues may occur up to 30 hertz. Think about, again, your handheld calibrator at 100 or 159.2 hertz. Is that going to find it? Maybe not. And wiring. Wiring can go bad from shock or over time. It can cause complete sensor faults or intermittencies. It could be amplitude-based. This could be within the sensor itself or externally. And we all know intermittencies are some of the most challenging things that we can face as far as sensor faults. It can be infuriating. But again, think to yourself, would a handheld calibrator catch this? Maybe, maybe not. So, like I mentioned before, resources that are available. There's a great paper that we love. It's available online. We're going to send a link to it. It's from 2008, 2009. It overviews fault types in a lot of types of sensors used across a big range of applications, you know, from thermocouples, resistance, RTDs, piezoelectric and piezoresistive based pressure, acceleration, force and strain sensors, and so many more. But it gives you a great start to investigate fault types for every type of sensor that you use. So it's almost a must-have and a must-read, even if you're just looking at the small section that deals with the sensor types that you have. So working towards the sensor risk, you really have to consider all the factors. Who has dropped an accelerometer in the past? A story that I love to give. One time when I was visiting a large facility, an engineer, it was a metrology engineer, and I were talking, we were leaving the metrology room, and ahead of us about 30 feet was an instrument cart that it just left the Cal lab. 3 sensor cases fell off the cart onto the concrete walkway, and the dude operating the cart just picked them up, put them on the cart, and started walking away. The engineer hosting my visit didn't really seem to notice, and we almost walked around the cart before I asked the question, well, what happens to these sensors now? I didn't learn the type of sensor that was used, but in my experience dealing with highly sensitive accels for the past 30 years, it kind of preconditioned my brain to recognize that those sensors should be retested. So think about your likelihood. Does your likelihood assessment consider factors like this when you're training all of the staff that deals with your sensors? And develop a recommended actions table. Here's just a basic example, but it starts to determine a risk score, which is basically the severity times the likelihood. And again, this is a little bit simplified and we use it kind of for our purposes internally, but you can use a risk factor matrix that works for you. But so based on that multiplied value, you can start assessing risk score and risk levels and determining if it's an acceptable risk that you can take or something that requires additional action, additional testing, or additional calibration. So we'll provide a copy of this. Well, it'll be included, but again, making both the risk table and the recommended actions table are something that you should, as an organization, determine. And now we're going to kind of go over some common sensor calibration intervals used with popular intervals. Like no periodic cal performed, that's fine. It's really great for sensors that don't make measurements, display units, demo units, or something that might show a level of performance, but the accuracy of data isn't important. It can also be used if the measurement instrument is unlikely to change. Think of something like a standard desk ruler. It's not likely that the ruler is going to drastically change, so perhaps no periodic calibration is a fine strategy. Fixed interval, calibrated annually, every 6 months, every 24 months. This is probably one of the most common methods for sensors. Why? It's easy. Intervals are often given based on experience and history. If some sensors in a group start acting up, it's easy to reel in that interval time. Or the opposite. You can extend it if a sensor hasn't changed over several intervals. The downsides, of course, can include inadvertently taking bad measurements if the sensor performance has changed, you might need to retest. And on the flip side, equipment may be calibrated too frequently, causing extra cost. A time and use method is primarily used for sensors that drift over time. It can be tough to implement, but essentially the number of calibrations varies directly with length of time the sensor has been in use. The biggest challenge with this is that it's tough to track. You can have wildly varying calibration times across sensor inventory, and the cost of timers can be high. But again, for any time-based sensor, this can be a strategy that's effective. Borrowed intervals, this one sounds too good to be true. Borrowing sensors that have been calibrated on a similar or acceptable method that fits your testing. Risk tolerances must be agreed upon, but it really can be an effective cal approach. Another example can be sensors rented for a project. Assuming your rental partner is reputable, the calibration challenge is already solved. An automatic adjustment method or staircase. This one is basically each time a sensor is calibrated, the next cal interval is lengthened or shortened depending on the outcome, on the accuracy result of a sensor based on an arbitrary permissible error used. Similar to the time and use method, it can cause a challenging and staggered workload, but can be effective, and many companies use this approach. And finally, control charts. They can be used as an as-needed basis to track behavior on a more frequent basis, weekly, daily, or even before and after a measurement. It's very time-consuming, but identifies when accuracy fails based on any number of factors, including the sensor, the environment, or even the operator. A daily calibration is often performed as verification for a working reference sensor when we use back-to-back calibrations in our lab. And a control chart of that working reference or the verification sensor is a method to tightly control such an important piece of the traceability chain. And traceability chain is kind of an interesting topic. It relates really closely to our bonus topic, what is considered a calibration. There's a lot packed into the NCSL definition. Whole presentations longer than this one are devoted to measurement uncertainty, which is the statistical combination of accuracy and precision. Developing a proper uncertainty budget comprised of systemic and random uncertainties, reporting coverage factors, and more probably topics too deep for today. But NCSL International is open to any organization interested in metrology, if they're the National Conference of Standards Labs. But really the note about traceability, using Excels as an example, what you're looking for is an unbroken chain of traceability from your measurement to a primary source, the base units. And your sensor may follow a similar path, but the unbroken chain to a primary source is usually very important for lab grade measurement. And then let's talk again real quick on the topic of field calibration. Calibration is a pretty funny word. Misused, it can cause some engineers involved in measurements to get really nervous. In other engineers, it may provide a security blanket. But if we consider field calibration, a lot of sensor types offer various methods to perform a quick check to use before or after taking a measurement, or to troubleshoot issues during a test. This handheld accelerometer calibrator is super popular, provides a portable fixed amplitude and frequency range. It's perfect for verification of an entire measurement chain. But what if you have a damaged sensor, like we talked about before, a deep bonded element, or it was dropped and there's crystal damage? With your field calibrator only providing at a fixed amplitude and a fixed frequency, are you going to be able to test for a damaged sensor every time? Think about that in the back of your mind, not to panic everyone. I don't want everyone to run from this presentation screaming that they're doing all the wrong things. But think about other options. Other devices may exist that provide additional functionality. Modal Shop makes this portable vibration calibration device that operates over a wide frequency and amplitude range, and it has a built-in traceable reference accelerometer. It can even create a traceable CalCert, but at a trade-off for uncertainty from sending it into a pro lab or someone using one of the Modal Shop, for example's Cal workstations. So when assessing risk, it's important to think about some often overlooked calibration-related factors. Were any on your recalibration or your initial calibration, were any specs omitted? Were there typical specs used? Was the sensor really fully tested when it was made? Was the last calibration good? Was it just done at a single point or a limited range? Is there historic or trend data available, and is it reviewed? And then this is maybe a goofy question, but it's important to think about, were any system or sensor adjustments made? And is it considered a calibration if no adjustments were made? We get that question from time to time, and the answer is yes. For our example that we're picking on a lot today, the poor accelerometer, it's a hermetically sealed unit. It offers no real chance to dig into it and make changes. A calibration is considered a calibration even though nothing was done to it before or after. The data is the same. So I'd like you to consider what calibrations included when you compare new to a spec sheet. We're just going to go over some of the basics here for this, again, accelerometer. Like the physical attributes section may not be really that important. That's likely not going to be tested when it comes in for any calibration. So maybe it's not really vital to you for the recal. The physical attributes are why you pick the sensor to begin with, but maybe not something that needs to have time spent on checking. The typical specs. These may be specs that didn't even come included with your sensor when it was built and bought. These often are done at a design phase at a really high level, take a lot of time to develop statistical data of, and are deemed that they're specs that won't change over time, even in the manufacturing process. What you're really looking for are the main attributes. Are they tested when you're getting your recalibration done? The overall sensitivity, the measurement range, and then the secondary specs also tested. Your resolution, nonlinearities, things like that. And then if things are important to you for other specs that are also important, it's kind of important to know from your cal provider what they're going to provide and what's important to you. I feel like some of the highlighting got off a little bit here, but in general. So would that same cal information be included in your recal? Ask yourself that, because that's part of your risk assessment. If it's acceptable, if it's not included. So really, we're just wrapping up here. The answer to how often you should calibrate is really still, it depends. it kind of is on you. To conclude, really, evaluate your existing cal program. Make sure you're aware of any time that your cal program didn't work for you. Start to keep track of those. Make a KPI or metric in some way internally, so you could say, well, remember that time when this happened. What can you do differently to avoid that risk? Understand your severity of outcomes of a bad test, the probability of a sensor or bad problems, and consider all stages. Again, think about that those poor 3 boxes that fell off the sensor card after the cal lab. Does that happen where you are? And I think it's easy for all of us engineers involved to say, no, that never happens. But sensors often just don't up and turn bad over time. But make sure you use a risk assessment matrix internally. The likelihood axis is often most solvable. Your risk elimination should evolve and improve as needed. Review your cal interval methods used, and create and utilize a recommended actions table. And basically, it's pretty short here, but that's it. Thanks.